Another new graphical feature about a rational function is the potential for the graph to have a hole in it. Definition-wise, these are basically points on a graph where the function does not have a vertical asymptote, but the rational function is still undefined at this point. Now, you guys have kind of seen holes in the past when we were talking about piecewise functions way back in the day, right? And a certain piecewise function would come, have a closed dot, and then open, and then would carry on. What's happening in this case is we're going to have a nice, what appears to be continuous curve, but at some location, right? So we have some vertical asymptote maybe, but at some location there is actually a hole in the graph. And so that's what I mean. What happens there is we're undefined like we are in a vertical asymptote case, but rather than having a vertical asymptote, the graph actually has a hole in the graph. So in this case, rather than the outputs being unbounded around that C value, around this capital C value, let's say, right, the outputs are actually going towards the same number. It's just that we're not actually reaching that number because we're undefined. So again, the reason why we're undefined has everything to do with the domain. All right, and so this is what's going to happen in this. So what you want to do to find the zeros is you first want to find your domain, just like you would to start this whole thing. Everything starts there. And then the second thing you want to do is simplify the rational function. So we do that by also factoring the numerator. So what are the zeros up in the denominator, and what are the zeros in the numerator? And if we find that we have a common zero, we've essentially found the location where we have a hole in the graph. And we locate that by evaluating the simplified function. So a lot of words there. Let's see it in action and go from there. So the first thing I want to do again is to find the domain. So essentially, where are my zeros down on the bottom? So if we take the bottom and we factor it, that's going to be x minus 4 and x plus 2. So the zeros down below, right, what we can't be equal to are 4 and negative 2 respectively. And so from our previous discussion, I would expect vertical asymptotes to occur at these two locations. However, when we consider the zeros up above, so again we'll go through a factoring routine, the difference of squares factors is x minus 2x plus 2. We see that up here we have 2 and negative 2 as our potential zeros for that. And right away, let me change colors, we notice that negative 2 happens to be 0 up on the upstairs and downstairs. So what this means, if we tried to find f of negative 2, we'd end up with a 0 over 0, which is a very weird situation. This is what mathematicians call undetermined, because there's a lot, division by 0 is undefined, but 0 in the numerator means we're 0, and then if we divide by the same thing, we get 1. So there's a lot of different interpretations of that, of what can potentially happen. What you also notice is that the factor x plus 2 cancels itself out, and so we can kind of rewrite f of x, and let me put it as an approximation, because this new function, x minus 2 over x minus 4, right, this behaves like this guy here because of the simplification, with the exception at negative 2. Notice we kind of got rid of the problem at negative 2. So there's basically what has to happen here. So what I now know is that there's truly a vertical asymptote at x equals 4, because that 0 didn't go away, but there's a hole in our graph at x equals negative 2. Because basically that 0 is also a 0 up in the numerator, and so it essentially effectively kind of cancels itself out. So that means we have a hole. So if applicable, right, and in this case it does, how do we find the exact location of this hole? Well, what we do is we take this simplified version and we evaluate it at the location of the hole. So when I plug that in, right, we're going to get negative 4 over negative 6. That reduces to 2/3. So the hole, the location of the hole on the graph is negative 2 and 2/3. So getting ready for where we're going to go, if I had to graph this function, here's what I know about it. So here's the y-axis and here's the x-axis. At 4, we have a vertical asymptote. It's multiplicity 1, so the graph is either doing this and then this, right? Or doing this and this, right? Let me use a different color there. So that's what we know so far. That we also know is that the location of the hole, let me make that 1, is at -2 and about 2/3. So there's a hole in the graph right about there. So there's a lot of other things we have to fill in about this graph. But as far as the graph is concerned, I know the graph is ripping itself apart at 4, behaving like a multiplicity 1, and then there's a hole in the graph. So, maybe the graph is doing this number, and doing something different over here, but there's definitely a hole in the graph. And so let's go ahead and go to technology to kind of see that in action. So here's the function. Let me turn that sucker on. And what you're going to notice, come on, turn on. What you're going to notice for this function, all right, is, so you can kind of see I had the graph a little bit wrong, but we'll fill in those details a little later. But what's important is at 4, right, at 4 we have the vertical asymptote, but right around x equals -2, notice that it seems to be, right, I think there's 1 right there, so it's right around what we can predict it to be is, so that's basically right around 2/3. And so the technology is actually showing us that the graph seems to be defined there, but we know, we're a little bit smarter than technology, that really what's happening there is there's a little bit of a hole. And what ends up happening too, I've always kind of experienced this with Desmos, but on your TI-84, if you zoom in on that hole area far enough, you will eventually actually see a gap in the function. Desmos won't do that, so I think that's a little bit of a glitch with regard to this. It's a great feature, but I think I found a little bit of a glitch. But we know, using our algebra, that at that location, there's actually a little hole in the graph. So I think I had my graph wrong. So it's doing this and it's doing that, but we know at that location there's a hole. So again, before we do another example, right, we basically find the zeros, the domain of the bottom. We basically find the zeros at the top, all right, and then wherever we find those, where we have a 0 common, that's where the hole is. We simplify, and then we evaluate where the hole is at by evaluating the function that's simplified. So let's go ahead and do that one more time. I think I have time, yeah. So if we do this one more time, the top, right, already has the factor 2x minus 3. So x equals 3/2 is a 0 for the numerator. Down below, if we factor that, I think what we'll get is that. So let's double check this real quick. 2 squared, 2x, yep, so we get that. And so you'll notice that x can't be 3/2 and x can't be -1. So right away, we can clearly see, right, that there's a 0 in common. So there's a true vertical asymptote at -1. It's multiplicity 1, so I know the graph is ripping itself positively and negatively there. But there's a hole in the graph at x equals 3/2. And so how do we find that hole? Well, we evaluate, right, our new function, if we simplify it, is approximately equal to 1 over x plus 1. So basically, I find what is f of 3/2. And so doing some fraction work down there, this is 1, this is 3/2 plus 2 over 2, this is 1 over 5/2, multiplied by the reciprocal, and we get 2/5. So the hole in the graph is located at x equals 3/2 and y equals 2/5. So here's where I expect a hole, and here's where I expect a vertical asymptote. And again, if we were graphing this by hand, right, at -1, I'd expect the graph to be doing something like this, right, in either direction. And then right around, here's 1 and 2, right at 3/2, I expect a little bit of a hole in the graph. So, maybe it's doing this or maybe it's doing that, but there's definitely a hole in that location. So let's turn to technology and kind of verify our algebra. So when I turn that function on, you can basically see what I just showed you. So at -1, right, the graph is truly ripping itself apart. So let me zoom out of there. All right, at -1, and it's behaving like a multiplicity 1. And then somewhere over here, let me zoom in. So there's 3.5, and what we get is 2/5 right there, because there's 2, there's 1, so we're about 0.4. right, is where that graph is. So again, the technology appears to show that the graph is defined there, but because of our work in our algebra, we know that there's a little hole in the graph. So we're coming up, going this direction, and at that location, at 3/2, 2/5, we have a hole. All right, so there you go. So vertical asymptotes and holes, they pretty much start the same because we're looking for zeros in the denominator, but then we're also now looking at zeros up in the numerator, and if we have any matching zeros, we found a hole. If we don't have any matching zeros, we truly have a vertical asymptote. All righty, so more coming soon.